Sorry for the interruption. So weighting of particles is a very important so weightability of particles is the very important parameter in formation of the metal matrix composite. And second is the particle distribution. Means the particle distribution should be uniform in the metal. So if there will be no weighting of particles with the molten metal, then the bonding there will be no bonding, leading to particles settling on the bottom. And from the particle distribution, if particle distribution is not uniform, that lead to clustering and agglomeration. That affect the mechanical properties, means the properties. So if we start from the weighting of particles, we can see the example from the heterogeneous nucleation also. Like this is the solid surface, means ceramic particles, in which this is liquid metal. So the surface energies defines a contact angle between the liquid and solid phases. Means liquid is the metal, solid is the ceramic surface. So this can be written as if the surface energies of these different interfaces is written as this is solid liquid, this is solid vapor, and this is liquid vapor, and the angle between this is theta. So theta is the contact angle between the liquid metal and solid ceramic. So if we write the equation, gamma LV equals to gamma SV plus gamma SL cos theta. So the cos theta will be gamma LV minus gamma SV divided by gamma SL. So the theta value should be low, means for the good weighting, contact angle should be as low as possible. For good weightability or good weighting. bonding. To ensure the wetting, if our ceramic particles do not wet with the liquid metal, then different chemical reagents or process are used to increase the wettability of the ceramic particles. So the wetting agents are can be added, can be the magnesium powder, silicon, and the nickel coating on the ceramic particles. Means the wetting agent are able to modify a surface to decrease the contact angle. So the magnesium powder can be added in aluminium melt, nickel coating on ceramic particles, and the heat treatment of silicon carbide to form a thin coating of silicon. Means the silicon carbide particles are heat treated before the addition to form a silicon oxide layer that will modify the wetting characteristic of these silicon carbide particles. So how this wetting is improved in the silicon carbide addition? So there are three steps. So first is the deoxidation of aluminium surface. To expose the fresh aluminium for the reaction. So the reaction can be written as 4 aluminium, which is in liquid state, plus Al2O3 solid ceramic particle, that gives the 3Al2O gas. So this will deoxidize the aluminium surface. Second step in this is the deoxidation of silicon carbide. Surface. So that will break the silicon oxide film then. So first is the silicon oxide layer is formed to protect the silicon carbide. Then in the process, the silicon carbide surface is deoxidized to break the silicon oxide layer to so that provide the fresh silicon carbide surface for wetting. And the third is the wetting through Al4 C3 interface. Means the Al4 C3 compound forms during this reaction that lead to good wetting. For aluminium plus 3 silicon carbide forms the Al4 C3 plus 3 silicon. So the Al4C3 layer deposits on the silicon carbide and alters the surface tension of the silicon carbide surface. Means this surface is the Al4C3. So this alters the surface tension and surface energy that lead to decrease in contact angle. So in this process also the Al4C3 formation is also limited. To surface because it breaks easily. So to avoid to limit the Al4C3 formation, silicon is further added in the melt, and silicon reduces, it suppresses the Al4C3 formation. At the same time, it provides the good wettability by segregating at the interface and forming strong chemical bond with silicon carbide. So now the silicon is added. So silicon forms a chemical bond with silicon carbide. That also lead to the decrease in contact angle. Next is the silicon coating. So how nickel coating enables the good wetting. So as the nickel coated ceramic particles are added, it will react, and the reaction is exothermic. Nickel will react with aluminium. So this is a exothermic reaction between liquid aluminium and after the reaction it forms the NiAl3, which is a ordered compound. So the ordered compound has the less interfacial energy. So the less interfacial energy lead to good wetting. And the nickel coating also enables the also prevent the oxidation of silicon carbide particles. So first is the silicon addition, the next nickel coating, and the final last is the magnesium addition. So magnesium also alters the surface tension of the ceramic particle and metal interface by reduce the interfacial energy. and the magnesium also disrupts the oxide layer between the aluminium and ceramic particles, enabling the good wetting of with the ceramic particles. Oxide layer, it then provide good wetting. The titanium can also be added during the modification of surface properties. So it leads to the absorption of titanium and form the, so it absorbs titanium and form titanium carbide particles, which has the good wettability. And the silicon also absorbs on silicon carbide interface and improves the wetting and improves wetting. So this is the wetting sorry. So this is the addition of different surface modifying agents to reduce the wetting angle. So by the good wettability, good bonding occurs between ceramic particles. And metal. So when the particle is bonded efficiently with the metal, enables the transfer of load, means easy transfer of load to the stronger reinforcement via the particle matrix interface, and therefore interfacial bonding must be strong. So how this, so why the good bonding is required, means with good bonding the load can be transferred from the soft matrix phase to the stronger ceramic phase, and the crack nucleation can also be restricted by the ceramic particles if the bonding between metal and ceramic is good. And next is the, so load transfer is easy. So due to the particle bonding, load transfer is easy, and the crack nucleation and growth can be stopped. So for the good particle bonding, particle interfacial bonding, the particle wetting and the solidification conditions are required, means the proper bonding depends on the particle wetting and solidification conditions. So the particle weighting behavior we studied. Now now is the solidification. So how the solidification uh, defines the proper bonding between ceramic and aluminium metal. So during the solidification, if temperature is high enough, is maintained high enough to ensure uh, better weighting. Means with increasing the temperature, the contact angle can also be decreased. If we draw a graph for aluminium silicon carbide composite system between the contact angle theta and time. So with the time, if we draw a 45, 120 and 135. 135 is the obtuse angle, means angle greater than 90 degree, which is not required for good weighting. So if the curve is drawn for the certain temperature, let's see for the 1073 Kelvin. So if the temperature is decreased, the contact angle will decrease. Decrease in contact angle will be slow, while for if we increase the temperature, let's say it's 1273 Kelvin, the decrease in contact angle is faster for higher temperature. Similarly, if we draw a curve between theta and temperature for the initial and final angle, means initial angle is the is 135 and final contact angle is 45. So with increasing temperature, the initial and final contact angle can also be decreased. So this will be the initial contact angle, then contact angle variation. This will be final contact angle variation. So the initial contact angle can also be decreased with increasing temperature. The temperature also, no, the solidification condition it also ensures the uniform distribution of the particles, means the distribution of particles should be uniform. So how can we ensure by uniform distribution of particles by the solidification condition? So this depends on the particle metal interaction during solidification. So during solidification, the temperature field exists in the melt, and from the temperature field, the temperature field creates by the heat flow from the melt. So the temperature field in heat flow makes the isotherms of melting point in the different region of melt. Isothermal isotherm lines of melting point of the matrix composite matrix material. And the isotherm lines of melting point defines the solidification front interaction with the ceramic particles. If the interaction is such that the particles are pushed by the solidification front, particles are pushed due to the pushing, clustering occurs. And if the particles are engulfed, means during solidification, that results in uniform distribution. So how the isotherm and the solidification front affects the particle distribution. So the isotherm line depends on the thermal conductivity of matrix metal and the ceramic particles. Metal and ceramic. So a ratio is defined between thermal conductivity of ceramic particles and metal, that is written as the alpha, which is the ratio of thermal conductivity of particles divided by thermal conductivity of metal. And the value of alpha defines the distribution condition in the melt. So the alpha values can be 1, less than 1 or greater than 1. So if alpha is equal to 1, the heat flux line, so flux lines lie along heat flow. Means flux lines are along the heat flow, and isotherms will be, so flux lines are along the heat flow, means that direction. So the isotherm of melting point will be in x direction. Like if we see, this is heat flow and this is isotherm lines. So if we see by a diagram, this is ceramic particles. So when alpha is equals to 1, the isotherm lines with the ceramic particles will be this type, straight. These are the isotherm lines. And when the alpha is less than 1 means particle thermal conductivity is less than the metal, then the isotherm line will diverge away from the particle. Means when the so the isotherm lines will be this type, means it will try to escape from the ceramic particles when alpha is less than 1. So that will lead to uh, pushing of particles, means clustering. If alpha is greater than 1, then the means the thermal conductivity of particles are greater than the metal. So the isotherm lines for the ceramic particles will be this will converge towards the particles, means the isotherm line will be of this type. And it will curve down with the ceramic particle surface. So means the alpha equals to 1 means the planar surface, planar interface. Alpha greater than means 1 less than 1 means the isotherm lines are deviated from their path with the ceramic particle. So for alpha less than 1, the clustering of particles will form and segregated along the when are you able to see the screen?
Yes, ma'am.
Sorry, it was not there.
Yeah, till now not visible, ma'am. Now only visible, ma'am.
Okay, you can ask whenever it is not showing.
Okay, ma'am. Okay, ma'am.
So or I will explain. So where you escape up to which point you were able to see the screen? Yeah, so I was
Mhm.
explaining the addition of different like powders, metal powders to modify the
Yes, ma'am.
uh, surface properties of
Yes,
ceramic
ma'am.
particles to enable the good wetting. So the
Yes, ma'am.
particle bonding with the metal ensure is very
The distribution of particles, ma'am.
yeah is
Yes.
okay. So distribution of particles we are there. This
The thermal field. Mm.
okay, the thermal field. Yeah, this from temperature field we I will explain. this distribution of particles, na?
Yeah, yes, ma'am. Yes,
Yeah,
ma'am.
so the to ensure the good particle and metal bonding, so the first is the wetting of the particles, second is the distribution of particles. That depends on the, so distribution depends on the particle metal interaction during the solidification process. So how the solidification process affect the this distribution of particles. So for during the solidification, and the heat flow from the melt, that will result in the generation of temperature field and the isotherm lines of melting point of the matrix material. Means when the if we see this is the melt, so heat is flowing outward from the melt. So the isotherm lines form along this x direction. If we see, let assume this is x z direction, so this will be x direction. So the due to the heat flow there will be a temperature field, and the isotherm lines will form along the x direction, and that will affect, that will generate the solid means so due to the heat flow the solidification starts, and the front of the solidification interact with the particles. Means the as the metal starts to solidify, the also ejects the particles. Means particles around the solidification front, and the interaction between that solidification front with particles enables the defines the distribution of particles. So if the particles are pushed by the solidification front, that will lead to clustering, and if the particles are engulfed by the solidification front, so engulfing will ensure the uniform distribution. Means the particles are within the matrix, so they are distributed uniformly. So how the solidification front defines the distribution? Means there we can see the thermal conductivity of metal and ceramic particles. So there is a ratio of thermal conductivity of particles and thermal conductivity of metal matrix, which is defined as the alpha. So it can have the values which is equal to 1, less than 1, and greater than 1. So when the alpha equals to 1 means the thermal conductivity of ceramic particles and metal matrix are equal. So flux line will be straight along the z direction due to the heat flow in z direction, and isothermal lines will be straight. So if we see the isotherm lines with the ceramic particles, it will also go straight with the ceramic particles. So this lead to the planar interface between ceramic and metal matrix. While if the and when the alpha is less than 1 means the thermal conductivity of particles is less than metal matrix, the conductivity of metal, then the isothermal line will diverge from the ceramic particle surface. Means it will try to escape out from with the ceramic. So due to the escaping, the solidification front will push the ceramic particles. So the pushing of particles will lead to clustering. And if the alpha is greater than 1 means the thermal conductivity of particle is greater than thermal conductivity of metal, then the isothermal lines will converge out at the ceramic particle interface. So due to the convergence of the isothermal lines, uh, so the convergence will allow the engulfing of particles within the in the solidification front. Engulfing of particles. So with the engulfing of particles, the particle will distribute uniformly in the matrix. So this is how we can see the effect of solidification condition to solidification condition effect on the distribution of particles. And this engulfing of particles and uniform distribution also leads to the homogeneous microstructure after the solidification. So this is the overview is completed. So I will go to the. Did you attended the assignment 9?
Yes, ma'am.
Okay. Yeah. So I will just share the assignment also. Yeah, you can give the answers here also. Means, for
Yes, ma'am.
question 1, it is asked that which of the following statement is correct about the composite. So first statement is the term composite broadly refers to material system which is composed of a discrete phase, means reinforcement, that is distributed in a continuous phase the matrix. So this is also correct. And second is it derives a combination of properties not attainable by the constituents individually. So this is second statement is also correct. Third is the MMCs combine the properties of metal like ductility and toughness with those ceramics with of high strength and stiffness. So all
Yeah.
three statements are
All three are
correct.
correct.
So the correct option will be D. In the second question, it is so which of the following uh, are the liquid state processing methods? Okay, so can you,
You are strip casting
yeah,
and spray deposition. No, PVD chemical. Melt infiltration.
yeah, melt infiltration and
Yeah.
spray deposition also it is.
Spray deposition. Yeah.
So 1, 3
One,
and
two,
4.
four. 1, 3, 4.
So next option is the which of is next question is asked the which of the following statement is correct about the melt infiltration method of processing MMCs. So first is the reinforcement is made into the porous preform.
It's a correct option, ma'am.
Hmm.
One is correct. Two correct.
Okay.
Third correct. Fourth is wrong one.
Uniform microstructure achieved. Yeah.
Yes, fourth also correct, ma'am. 1,
Yeah,
3.
all options are correct.
Yes, ma'am.
So in the fourth question, it is asked that in which of the following are you able to see the question?
Yes, ma'am. Yes, ma'am.
Okay. So in which of the following processing method of MMCs high mechanical or electrical energy is applied for a short time of consolidation?
High energy, high rate, ma'am.
Yeah, correct. So next question. So in this steps we have to arrange by followed that is followed by physical vapor deposition method of processing MMCs.
The first vapor generated by the high intensity electron beams.
Yeah.
Second, fibers are passed through the chamber filled with a vapor of matrix material.
Yeah.
And third, assembly of coated fibers into the bundle and then hot pressing or HB.
Yeah.
1 to 4.
Yeah. Correct. So next question is the which type of processing method of MMCs has been used to make the 6061 aluminum boron fiber composite?
I think, yeah, melt infiltration, ma'am.
No.
Uh, diffusion bonding.
Yeah, diffusion bonding in which
Okay.
the boron
Yeah,
fiber are coated with the 6061 aluminum.
yeah, fiber means diffusion.
Huh.
Okay.
Next question is the precursor used to form in situ aluminum titanium diboride composites are?
Right. I think K2 TAF6 and KBF4
Yeah, that is correct. Means these are salts.
salts as well.
Hmm. So next question is the liquid does not weight the surface of the solid if the angle of contact is?
I think 0 or acute angle.
No.
Yeah, 0, ma'am.
No. When it is 0, then complete weighting will be there.
I mean, 45 degree.
Means it is asked that the liquid does not weight the surface.
Sorry, ma'am. I didn't know.
Means the correct answer is obtuse angle. Means obtuse
Okay, okay, okay.
will be greater than 90. So
Okay,
theta
miss.
should be
Greater than
less
90
than
means
all should
nickel plus
always
plus.
less than 90 degree,
Okay.
and acute angle is less than
Okay.
90 degree. So
Yes, sir.
for all three first three options, the liquid will weight the surface, while for obtuse angle, the liquid does not weight the surface. So next question is the what are the advantages of particles which form in situ during MMC's processing?
So, three, 2, 3, 4, madam. Clear interface between the particle and matrix.
Hmm.
Particle matrix bonding is good.
Huh.
Particles are finer and uniform distributed in the matrix.
Yes, correct. And the next question is the wettability of the dispersoid in the matrix has been improved by? So what are the different methods to improve wettability?
Modifying the surface energy.
Huh.
Addition of elements with increase in surface tension of the aluminum.
No, modifying is not this first option is not
Increase
correct. Miss, this is increasing contact angle which is not required.
if the contact angle is increased means it's not with, ma'am. Is it correct?
Sorry,
If contact angle is increased means
the
the the
wettability will decrease.
decrease.
Means here if it is there decreasing is written, then in this option will be correct.
Putting the whole surface element to the sorry, no, I didn't.
So,
I think last option, addition of elements with increasing the surface tension of the aluminum melts, it's increase the wettability.
no, the surface tension should also be low.
Decrease of the, okay. Processing temperature, ma'am.
Yeah, increasing processing temperature is correct.
Temperature
And
and formation of intermediate
yeah,
reaction product or surface to
means Al3Ti are formed during the process, and
distribution of aluminum oxide layer formed on
yeah,
the
this
disposed
destruction of
surface.
aluminum means
What?
the
Okay.
surface should be deoxidized. And
Okay.
the second option is also correct, coating the dispersoid surface which has the good wettability. So
Till
correct options
formation
are
it is two,
second,
three, four, five.
2, 3, 4, 5. Okay, so do you have any doubt in for this
Yeah.
session?
No, madam. I will go through it and check it, madam.
Okay, thank you.
Okay. Thank you, madam.
Okay, so good evening all. So today is the week 9 problem solving session. So in the up to week 8 we studied about the different aluminium alloys, their properties and physical metallurgy of aluminium alloys, and the green refinement methods and the uh, strengthening methods of the aluminium alloys. So now we will start the aluminium based metal matrix composites. So the aluminium based metal matrix composites. So the aluminium matrix composites are made to improve the hardness and wear resistance of the aluminium alloys. Hardness and wear resistance. So what are the composites? So composites are made of two types of by combination of two materials. To obtain the mixed property combination of these two materials, means the metal matrix and plus ceramic as reinforcement. So the properties which are not attainable the combination of properties which are not attainable in the single material is we can obtain those properties by adding the metal and metal with reinforcement. So while composites can be made using different matrix like metal matrix, ceramic matrix, and the polymer matrix. So matrix can be any type of material, metal, ceramic and polymer. So in this course we will focus on the metal matrix. So metal matrix can be of different metals aluminum, copper, iron, magnesium, in which in this course aluminum alloy metal matrix are focused. So from the metals, metal matrix composites, ceramics are added. So from the metal, the ductility and toughness comes, and from the ceramic particle reinforcement, strength comes in picture, strength and stiffness. And the specific properties of aluminum alloys, such as specific strength, density, can be improved by making the aluminum matrix composites. The aluminum matrix composite can also be written as the AMCs. So AMC has the low density, high specific properties, high corrosion resistance, and the availability of aluminum also allows the aluminum metal matrix fabrication easy. Means the aluminum availability is and it is also cheap and available in the market. So the metal matrix composites of aluminum can be easily made or prepared. So how to manufacture, so the fabrication of aluminum metal matrix, fabrication processes of AMCs. So there are different processes by which the AMCs are made, and that depends on the state of the matrix also. So the AMCs can be made via liquid state process, solid state process, or vapor state process. So in the liquid state process, three types of processing methods are used. First is the stir casting, second is melt infiltration, and the third is spray deposition. In the solid state processes, first comes the powder metallurgy route, diffusion bonding, and the high energy high rate. And the vapor state process has also three types of methods. First is the chemical vapor deposition, physical vapor deposition, and electron beam physical vapor deposition. So we will study all these processes one by one. So in first we will start from the stir casting process. So in stir casting, hello, hi Mohan. Do you have any doubt regarding the week 9 lectures? Mohan, are you able to listen, hear my voice?
Yes, ma'am.
So do you have any doubt in week 9 lectures?
No, ma'am.
Oh, so can I proceed with the overview of the all lectures?
Okay.
Okay. So in the week 9 lectures, we studied about the aluminum based metal matrix composites. So the composites are made to enhance to obtain the mixed combination of properties which cannot be attainable in the single material. So in the composites matrix can be of three types, means all three materials, metal, ceramics and polymers can be used as a matrix, and the reinforcement can also be chosen from the ceramic and polymers. So from the metal matrix, the aluminum based metal matrix composites are focused in this course. So the metal matrix composites, by the metal, ductility and toughness comes in the picture, and the from the ceramic particles, strength and stiffness comes. So the combination of all these four properties can be obtained in the composites. So why the aluminum metal matrix composites are made? Because they have the low density, high corrosion resistance, and the availability of aluminum also lead to the fabrication of aluminum metal matrix easily. So there are different fabrication processes of these aluminum metal matrix composites. First, depending on the three states of the material. So according to the liquid state, three types of processes are used. First is the stir casting, second melt infiltration, and third is the spray deposition. So these are the liquid state processes. In the solid state process, the powder metallurgy, diffusion bonding and high energy high rate process is used to form in fabrication of the metal matrix composites. And in the vapor state process, the chemical vapor deposition, physical vapor deposition and electron beam physical vapor deposition process are used. So I am starting from the stir casting process. So in the stir casting process, the melt during casting is stirred from a mechanical stirrer. Means first the stirring of melt is done. Then during the stirring process, the ceramic particles are added. Ceramic particles. So if we see the diagram, so this is the male, this is the stirrer. So the ceramic particles are added while stirring process, and this melt also protected by argon gas to avoid the oxidation of the melt. Prevent oxidation. So the due to stirring, the vortex generates in the melt. So that vortex help in the uniform distribution of particles. In the melt. So the process parameters of the stirring process, stir casting process are the stirring speed,
temperature,
dipping length, third is the melt temperature.
melt, pouring,
Uh, uh, Mohan, can you switch off your microphone?
okay, ma'am.
Melt temperature and the pouring temperature. Fifth is the impeller design. Impeller are used to stir the process. Stirring melt. So the stirring speed also by controlling the stirring speed, we can ensure the complete mixing of the ceramic particles. Dipping length of the stirrer controls the vortex formation. The melt temperature and pouring temperature defines the proper bonding and interaction between the ceramic particles and the metallic molten metal. And the impeller design, which is used for stirring melt, used to create used for the easy creation of the vortex. This is the creation of vortex. So by controlling these parameters, we can enhance the stir casting the addition of ceramic particles in the stir casting process. So what are the advantages of stir casting process are? It is simple and cost effective. And disadvantages means there are many numbers of particles, many number of process parameters. Means different the process parameters control will be difficult. All so number of parameters are high. Second is the particle rejection. means if the particles does not weight particles do not weight from by the molten metal, then clustering of the ceramic particles occur. And the third is the gas porosity, means when the vortex is formed, the introduction of environmental gases also create the gas porosity in the molten metal. So these are the disadvantages of steel casting process. So in the aluminium metal matrix composites, the uh, reinforcement types are oxides, nitrides, borides, and this the others, means the oxide, nitrides, porous and carbides are added as a reinforcement in the aluminium matrix composite. So in the oxide, the Al2O3, TiO2 and ZNO and SiO2 are used. In nitrides, titanium nitride, silicon nitride and boron nitride are added. In boride, titanium diboride and Ti3C2, ZrB2 added. In the carbide, titanium carbide, silicon carbide are added, and in the others the sulfides comes, tungsten sulfide and diamond. So these are the different types of ceramic particles added in the aluminium metal matrix composite. So the next process is the melt infiltration. In the melt infiltration, the preform is made of ceramics. Preform of ceramic is made first. Then in the preform, the molten metal is poured. Or filled in the preform. That is porous. So the molten metal goes through the porous preform by the capillary forces. So the introduction to of molten metal in the preform can be done using pressure or without pressure. With or without pressure. So capillary forces are used to weight the for weighting of molten metal to ceramic preform. when pressure is used, and so the hydraulic pressure melt infiltration is called the squeeze infiltration. When a hydraulic pressure is applied, then it will the squeeze infiltration. So the weighting of ceramic preform is very important in this process, and that depends on the composition of molten metal also. So the advantage of the melt infiltration process is the near net shaped product can be made. Means when the preform is ready, only the filling of those pores are required, so that will obtain the near net shaped components or parts. And due to the distribution of porous structure of the preform, uniform microstructure is obtained. Means the ceramic particles are already throughout the matrix, so that is useful for the for attaining the uniform microstructure. And the limitation of this melt infiltration is the self-supporting preforms are required. If the preform is not able to self-support, then the melt infiltration process will be of no use. Structure required. Second is the damage of preform can occur during the process. That deteriorate the properties. Means during the filling of molten metal, the preform can also damage, that leads to the uh, the accumulation of the damaged parts in one section, that will deteriorate the mechanical or physical properties of the part. So these are so next is the spray deposition, which is last of the liquid state process. So in spray deposition, spray of molten metal is done. This is the melt. So this is metal. So this is the molten metal. This is sprayed in the chamber, and the ceramic particles are added during the spray process. So the ceramic particles interact with the stream of the metal and form the good bonding with the metal, and then the this Bonded ceramic and metal particles are deposited on the substrate in the at in the spraying chamber only. Then that and the remaining is remaining stream is collected in the this spray powder chamber. So this process also called the Osprey deposition. So these are the liquid process methods. Next are the solid state process. So in the solid state process, the powder metallurgy route comes first. So in the powder metallurgy, first is the mixing and blending of metal and ceramic powders are done. Means mixing, blending of metal and ceramic particles. Then the mix are compacted in the desired shape. Then that desired shape is further sintered to achieve the tensed part. So in the sintering process, hot pressing are also done. Sintering is done at high temperature. So the compaction and sintering can also be done in a single process, which is known as the hot isostatic pressing, which is more efficient than the simple sintering process, to achieving the approximately 100% density. Next is the high energy, high rate process. So in high energy, the mechanical and electrical energy is applied rapidly for the consolidation of the metal and ceramic particles. Means the first the metal and ceramic particles are mixed, and though that metal matrix powder mix is consolidated using the high energy for a very short time period. So that short time period leads to the compaction of the metal and ceramic particles. And it also lead to a rapid heating. So in the high energy high rate process, the phases in the material can be controlled, and grain growth can also be restricted in this process, because it is only because it is high rate process, only the high energy is applied for a very short time period. So the consolidation will happen so much fast that the phases cannot be altered, and the grain growth can also be controlled. So the for aluminium and silicon carbide composites are made through this process. Next is the diffusion bonding. In diffusion bonding process, the ceramic particles ceramic fibers are laid between two metal foils, means if these are two metal foils, the ceramic fibers are laid between these two metal foils. Similarly, this process is done. So it is also called fiber foil method. And the bonding between these two the alternative layers of metal and fiber is done at higher temperature. Bonding by diffusion at high temperature. So the 6061 aluminium, which is aluminium silicon magnesium alloy, with the boron fiber is composite is made using the diffusion bonding process. The diffusion bonding process can also be done by the deposition of metal on the fibers, means the fibers are coated with the metal, then the curing and evaporation of this metal by using any energy source is achieved. So this is also called the evaporating and depositing process. So next is the physical vapor deposition, vapor state process. In this physical vapor deposition, so in which the ceramic fibers are fed into a chamber in which metal vapor is prepared. The metal vapor deposit on the ceramic fibers and form a bond between the means the coating of metal on fibers done in the chamber, then those fibers are consolidated using a hot pressing. So if the vapor are generated using electron beam, then it is called electron beam physical vapor deposition process. And in the CVD process also, chemical vapor deposition, the fibers are coated by the are coated with metal by chemical reaction. So from these processes, a wide range of aluminum metal composites are made. So the next process is differing from these are two. I mean the state of the different processes are the first is the liquid, solid, and vapor. But the combination of liquid and solid state can also be done. Can also be used in the fabrication process of the AMCs. That is called in the two-phase processing. Means the metal is present in the liquid and solid state. So if we see this process in the spray deposition method, in which liquid metal is fed into the chamber by streaming. So the ceramic particles can added in the liquid stream, or if the stream is falling down, so the it will start to solidify. So in the solid stream of metal, ceramic particles are also added. So in the two steps, the ceramic particles are added in the molten metal stream and the solid. So the molten metal with ceramic and the solid metal with the ceramic particles interact and deposit on the substrate. So this is called as the variable co-deposition of multiphase material. Co-deposition means the liquid drops and solid particles are depositing at the same time. Multiphase materials. So the angle of addition of these ceramic particles also affect the uh, ceramic particle interaction, sorry, ceramic metal interaction, and depends on the uh, and affects the distribution and volume fraction of particles in the metal. So angle of the injection is the process parameter in this process. In the steel casting process, as the temperature goes down, this molten metal starts to solidify, and so and the liquid and solid metal exist at the same time, and the melt will be called as the mushy state zone. Means the liquid here is the mushy type, means the solid and liquid metal is present at the same time. So during this state, the particles are added in the steel casting process. So the mechanical stirrer helps in the better distribution of ceramic particles. So due to the mechanical stirring during liquid solid state enables the non-dendritic structure, means because the stirring breaks the dendritic fronts, leading to the broken dendrites, and so the broken dendrites will lead to the uniform and equiaxed microstructure. We studied the effect of stirring we studied in the grain refinement methods, like the due to the stirring the dendrites broke and leads to the more grain refinement. So equiaxed microstructure is formed. So depending on this two-phase material processing, the particles added in the during the process or after the process. So after the addition of ceramic particles after process is called the ex situ addition. Called the ex situ. So in the ex situ process of ceramic particle addition, the rejection of particles increases by the metal increases, and that lead to the agglomeration and clustering of particles at some certain regions. So if the ceramic particles are rejected, that lead to agglomeration. So again, the agglomeration is not required in the uh, formation of the metal matrix composite, as it affects the mechanical properties. So the very so control of process parameters should be very carefully to ensure the proper mixing of ceramic particles during ex situ addition. Ensure homogeneous distribution. While in the in situ process, the particle agglomeration can be eliminated. Means the in situ process helps in the homogeneous distribution of particles during the process only. Also, the particles should not be added uh, externally. The particles generated in during the process only in the in the metal. Like the if we see the example of aluminium and titanium diboride composite. So the titanium diboride particles are created in the molten metal by adding the different types of salts and compounds during the molten metal before the solidification. So the precursor of the titanium and boron are added first. So what are the precursors? Precursors are the different types of salts that are easily available. Means the salt like as the KbF4 and K2 TiF6. So these two salt first is contains the boron, second contains the titanium. So these two salts are added in the molten aluminium. And by the dissociation of these salts, the titanium and boron elements are obtained, and they form by forming and further forms the titanium diboride ceramic. So the required a proportion of these salts should be maintained to achieve the desired composition of the titanium diboride in the matrix composite. So the reaction can be written as in this process is written as the aluminium KbF4 plus K2TiF6. So that lead to the reaction of KAlF4 plus K3AlF6 plus TiB2. So TiB2 adds TiB2 means mixes with the aluminium, and these two salts which are formed after reaction are collected in the slag. So aluminium plus titanium boride composite is achieved by the reaction of these two salts. So this is called the in situ addition of ceramic particles. So this in situ process enables the clear interface between ceramic particle and aluminium. The clear interface because it is formed in the melt only. Clear interface that lead to good properties, and the bonding is also good. Particle and matrix. So in this process fine particles are also generated. So due to fine particles, fine microstructure is obtained. Similarly, the aluminium titanium carbide can also be uh, fabricated during the same in situ according to similarly to the titanium boroid, but the reaction in this process is different. The titanium carbide is also a strong particle. So in this process the K2TiF6 salt with graphite powder or carbon is added. And the reaction between this follows the 3K2TiF6 plus 4 aluminium gives 3. This reaction will give the 3 titanium plus 3KAlF4 first reaction, and the titanium dissociated in this reaction will react with aluminium forming the Al3Ti intermetallic. This Al3Ti dissolves and give titanium again, and this titanium add with the carbon from the graphite powder addition forming the titanium carbide. So in this process the Al3Ti intermetallic is not required in the metal matrix composite because it is brittle. So in the process the aluminium Al3Ti should not be present, while Ti titanium carbide should be formed more efficiently. Means titanium carbide should be present at the expense of the Al3Ti. Similarly, the master alloys can also be formed by this process. So how how to ensure that the Al3Ti is not present and titanium carbide is present. So the controlling the temperature and time during the process, during the reaction, helps in the controlling of the presence of these two phases. Means Al3Ti is not required while titanium carbide is required. So temperature should be high and temperature time should both be high to ensure the formation of titanium carbide particles. So how the ceramic and metal matrix formed by the bonding between these ceramic and metal. So for the good bonding, weighting of particles is the first requirement.